Okay, we're going to look at a galvanic cell and understand the different parts and how it works. So here I have two beakers of a solution. In this beaker, I've got, let's say I have silver nitrate, and I'm just going to show the silver ions. And in this beaker, let's say I have magnesium nitrate, so I'm only going to show the magnesium ions. In this first beaker, I'm going to put a piece of magnesium. And in this beaker, I'm going to put a piece of silver. Okay, now in one of these reactions, in one of these beakers, a reaction is going to occur. The metal is going to, the magnesium ions are going to form, and the silver is going to plate out onto the magnesium. So the silver is going to become silver metal, the silver ions, and the magnesium is going to become magnesium ions. You might remember from an earlier chemistry class that magnesium, we said magnesium is more active than silver. So this is going to be spontaneous. Well, what about the reverse? What if I put silver into magnesium ions? Well, this is going to be non-spontaneous. That reaction is not going to occur. And we want to kind of see why. So this is not going to happen. So we could say that silver, we could see that silver, the silver ions, they want to get the electrons from magnesium. So silver is more hungry, not a very good chemical term, for electrons than magnesium. And we can compare any two metals this way. And so we're going to look at this right here. So we see that what happens is magnesium is going to become magnesium ions plus 2 electrons. And then the silver ion, we can balance this by putting 2, is going to become, it's going to gain 2 electrons to become silver metal. And I'll put a 0 on magnesium to show that it's neutral. So here magnesium is lost 2 electrons, we call that oxidation. And silver gains 2 electrons, we call that reduction. Okay, now we can see that electrons are transferred, and that's the important part we want to look at here. We want to look at what's going on with these electrons. And so we can actually set up a situation where we can harness those electrons that are moving. That's what we want to do. And because we have electrons that are moving, we can harness those electrons and we can use the electricity. And you do this all the time. We call it a battery. So on the left here, and it's very important what goes on the left, I'm going to have magnesium ions, and I'm going to have a strip of magnesium. Draw that a little better. So here is magnesium metal. Get it right the third time, hopefully. Okay, so here's magnesium metal. And over here, I'm going to have silver ions. Let's say it's in silver nitrate. And here's a piece of silver metal. Okay, so here's my solution. And we could say we've got nitrate as our counter ion. Now, if I were to connect these with a wire, you could see that electrons could flow. The only problem is this isn't a circuit, we've got to have, if electrons or charge is going to flow, it's got to go in a circle. We can't have more electrons on one side or the other. So what I'm going to do is put in what we call a salt bridge for something that ions can flow. It could be even a piece of paper saturated with ions. And so this is called a salt bridge. And it's what's going to allow ions to flow the opposite directions. Usually it's something that's not going to react, things that are always spectator ions like KNO3. Okay, so what's going to happen here is the magnesium, if we look up at our original equation, the magnesium is going to go from the solid into solution as magnesium ions. So magnesium is going to lose 2 electrons. So over here we have what is called oxidation. On the other hand, silver wants to go on and become silver metal, silver ions to silver metal. So it's going to have to pick up 2 electrons. So what's going to happen is as magnesium loses 2 electrons, those electrons travel this way towards the silver. So there's actually a force we call electromotive force that grabs the electrons off the magnesium and takes them over to the silver, where the silver then grabs them. And so what happens over here is silver is reduced. And now that we have electricity flowing, that's what electrons, we have electric current, we can measure the volts of this particular, what we'll call a cell. And, you know, it could work like a battery. You could put a light bulb there and it would light up. Okay, so some very important terms that are new. This electrode over here is called the anode. It's always on the left, and that's where oxidation occurs. On the right, we have the cathode, and that's where reduction occurs. So we want to be able to label the cell as we have it over here. Then we're going to write our half reaction. So magnesium is being oxidized. It's losing 2 electrons. And that, again, is on the left. And on the right, we have silver, which is gaining 1 electron to become silver metal. Okay, so oxidation on the left, reduction on the right. Now we want to write out a little equation, a little shorthand method. We've got magnesium 0 going to magnesium ions. So that's how we show that. Then we've got our salt bridge. That's what this is right here. And then we have silver ions. I'm going to go ahead and put the states here. So this is solid, aqueous, and silver going to silver metal. Okay, so this is kind of our shorthand method of what we've drawn up here in this electrochemical cell, and we want to be able to do that. Okay, one more thing and we're done. I want to figure out what is the voltage, and that's what we call E0 of the cell. What's the voltage? What would this say? What would the voltmeter say in volts? Okay, and there's a little table that we can look up the half cell of silver and the half cell of magnesium at 1 molar. The E0 of the cell is equal to E0 of my cathode minus E0 of my anode. Again, those are both going to be looked up, but it's very important that we remember this equation. So we're going to look up E0 of silver. That's going to be 0.80 volts. It's in the table in the book. And I'm going to subtract that of magnesium. Magnesium is minus 2.37 volts. And when I do that subtraction, I get 3.17 volts. And it must be positive to be spontaneous. So now we've looked at how to draw an electrochemical cell, a galvanic cell, or also known as a voltaic cell, and calculate its voltage.